The purpose of Lesson 2.2 is to graph transform versions of power functions, with a specific focus on quadratics since we're more familiar with them than other types of power functions, but the process for the most part isn't different between other types of power functions. The reason we want to look at this is that transformations can make visualizing different types of graphs a lot easier, and it can help you differentiate between what parts of the equation are responsible for the graph's shape as opposed to the graph's size. So what exactly are transformations? For our purpose, transformations are arithmetic operations like adding, subtracting, multiplying, and dividing that are put on a function that alter the patterns as well as affecting the dimensions and positions of a graph. In algebra, the graphs that we study are different from each other because they all use different special algebraic operators. These include exponents, an exponential base, logarithms, and trig expressions. There are other things that can constitute a function, but that's mostly what we look at this level. The algebraic operators of these functions determine the shape of the function when we reproduce the pattern on a graph. And each of these algebraic functions can have different arithmetic transformations put on them that will affect the size and the position of the graph, but not fundamentally change its shape. Functions are generally shown in the following two ways. On the left, we have the general form, a version of a function that uses placeholder variables to show all the possible transformations a function could have. Looking at our quadratic function x squared, the general form for this reads f of x equals a times x minus h squared plus k. Our three placeholder variables a, h, and k are responsible for different transformations of the shape of the quadratic function. Numbers that are in the a position are responsible for vertical dilation. This creates a visual effect on the graph that makes it appear to stretch out, as all of the output values end up getting multiplied by whatever you have in the a position. H and k are both translation transformations, meaning that the origin of the graph for x squared, we normally think of that as 0, 0, gets moved either left or right depending on the value of h, and or up and down depending on the value of k. If all three of these are set to their identity values, a being 1 and h and k both being 0, you just get plain old x squared. This is what we call the parent version of the function, where all the transformations are either 1 or 0, and this is what you generally think of as the most basic version of the function, where the only thing you get is the shape that's determined by the algebraic operator. For this assignment, our goal will be to create a table of 5 values and draw the graph of each function that we're given, as well as state the transformations that this graph has that differentiates it from the parent function. The first graph that we should make sure we look at is the parent function itself, f of x equals x squared. Again, there are no transformations on this, meaning that everything that we put into this function simply needs to be squared to give us the output. The table that I have to the right has the coordinates -2 and 4, -1 and 1, 0 and 0, 1 and 1, and 2 and 4. Let's see what those look like plotted out. So these 5 points give us the following graph here. The table that we have here for the parent function is what I will be referring to as the parent table for the quadratic function for all the future assignments. The x values here that we're using, -2 to 2, are a pretty common set of x values to use for a parent table. They're the ones that you want to use as often as you can, though a lot of the functions have a lot of strange restrictions that don't always allow us to do this. For the majority of power functions, though, -2 to 2 is a really good set of 5 x values to just get a good picture of the function. It allows you to see both the negative and positive sides of the x-axis, and uses small enough values that are easy to calculate that you can usually find these values really quickly, even if you don't already have them. So over here we have the function x minus 2 squared minus 3. This time we do have some transformations that we want to figure out, and we also have to create a table of 5 values and draw the graph of the function. The light gray line that we have on here isn't the function we're trying to draw. Instead, that is the parent function x squared. I put these on each of the graphs for this assignment so that when you graph your version of the function, you can see what the transformation looks like in comparison to the parent function on the same graph. As far as the function we have here goes, there doesn't appear to be anything sitting in front of the parentheses set. But as we saw in Unit 1, we know that if there's no multiplier in front of a parenthesis, we can think that that is secretly 1. Since 1 is the identity value for a, that means there's no vertical dilation on this graph, and we don't need to worry about multiplying our y values or anything like that. We do have values in the h and k positions of this function, so we will need to apply some translations. Specifically, the h value of 2 here means that we're going to be shifting our graph to the right 2, and our k value of -3 here means that we're shifting the graph down 3. We can talk more exactly about what these mean once we've got the entire equation plotted out in graph, but let's go to our steps here to fill out the table. So if you want to graph a transform function and get all the transform values for the table, the easiest way to do that is to start with the parent table of the function, the -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4 values. Then take all of the y values in the table and multiply them by a. Again, since our a value is 1 for this question, we don't need to do this step. Next, we want to add the opposite of h to all x values. So what do I mean by the opposite of h here? Well, you might have noticed in the transformations that I mentioned that the graph would be shifted to the right too, which we normally think of as moving in the positive direction. This seems strange because in the problem here we actually have a -2 sitting here, which might make you think we're moving to the left or subtracting from our x values. This is kind of a confusing thing about transformations, and the easiest way to describe it is that in the general forms of a lot of these things, there's a minus built into this formula, similar to what we saw with point slope form, where if we wanted to take the initial point of the graph, we needed to switch the sign on our x value here. The same is going to apply for our horizontal shifts, meaning that we want to regard x minus 2 as an h value of +2. So we'll be adding +2 to all of our x values for our table. This gives us new x values of 0, 1, 2, 3, and 4. Now you can see even though there's a minus built into the general form of the quadratic here, there's a plus built on the outside for k, meaning that we do not need to switch the sign on whatever number we have out here as we add k to all of our y values. So in this case, we'll need to subtract 3 from the values we have here. This gives us a new set of y values of 1, -2, -3, another -2, and another +1. Now I just need to take the x values that I have here in blue and the y values that I have here in green and make them the new set of coordinates for our transform graph. And here's our transform graph with those 5 points plotted. You can see the 5 points we have are technically all spread out in the exact same fashion as the parent function, with 1 point at the origin, 2 points that are 1 away and 1 above the origin, and 2 more points that are 2 away and 4 above the origin. The difference here is that our origin has moved from 0, 0 down to 2 and -3. Remember that we also call this point the vertex of the parabola. Let's try a more difficult one. So here we have -1/2 times x minus 4 squared plus 3. This time it looks like we have all 3 of the transformations. In our a position we have -1/2, in our h position we have 4, and in our k position we have 3. So we know from the previous problem that our h value of 4 and our k value of 3 are going to move us right 4 and up 3. So we're probably going to have an origin that's to the right and a little bit higher than where we see it now. That's why this graph is kind of pushed over from the other one. It's not as centered. The a value we have is a vertical dilation, which we didn't see in the last problem. For now, we can list that as a dilation by 1/2. But there is another mystery here in that the dilation value is negative. Is that going to have a different effect from a regular a value? Well, before we get to that, let's go ahead and just apply all the transformations to the table values and see what we come up with. If the first thing we're expected to do is multiply all of our y values by a, that means we're going to need to take our set of y values from the parent table, which we have here, and multiply all of them by -1/2. This is ultimately going to give us transformed y values of -2, -1/2, 0, -1/2, and another -2. Next, let's apply the shift right 4 by adding 4 to all of our x values. This gives us x values of 2, 3, 4, 5, and 6. Finally, we can apply our shift up 3 by adding 3 to all of our y values. It's really important that if you have both a and k in one of these problems that you apply the a value transformations first and add the k value transformations second. This is the same as following order of operations. Ultimately, the ending y values that we come up with are 1, 2.5, 3, another 2.5, and another 1. And here is our points plotted with our transformed quadratic function. With everything plotted here, we can now actually see what the negative did to the graph. Our graph is clearly upside down from the parent function, which as a transformation we call a reflection. Anytime a is negative, it's still going to be a dilation by whatever value you have for a, but it is also going to include a reflection over the x-axis. So there we have our transform table of 5 values, our transform function, and our transformation statements. Let's take a look at Desmos for a second. If plotting the tables gets confusing or taxing, or maybe you just want to look at a visual representation of what the transformations are like on Desmos in order to get a better picture of what you're trying to do, this file here, which I've called the Unit 2 Power Function Grapher, because we'll probably be using this for more than one assignment, is going to be the best tool here. You can see up top, I have a general form function here. Instead of having the 2 here in the quadratic function, I've got an n, which actually allows us to change what type of power function we're looking at. We'll talk about this more later. For now, you just want to keep this set at 2. You can also see we've got the vertical dilation, the horizontal shift, and the vertical shift values right here, which you can change. These sliders are set to move them by whole numbers, so if you want a fraction, you can always type it in. The last function we looked at, for example, had an a value of -1/2, a horizontal shift right 4, and a vertical shift up 3. So not only can you see what the transform graph looks like on here, but if you click this coordinate button, you can also see the transformed coordinates from the parent table, and you can just plot these directly onto your paper. So this will basically create all the tables and do all the graphs for you if you want it to, but that is your prerogative. That's all for now. See you soon.